Welcome to the deep dive. If you are tuning in today, you already know the premise of what we do here.
We take a dense, potentially overwhelming stack of source material, and we just extract the foundational architecture.
Exactly. We are targeting you, the learner, the kind of person who is, perhaps prepping for a high-level meeting, trying to catch up on a highly technical field, or just driven by this really intense curiosity to understand the mechanical reality of the world at its most fundamental level.
Right. And today's mission is definitely designed to conquer a subject that carries a lot of intimidating academic baggage.
Oh yeah, massive baggage. We're looking at nuclear chemistry.
Just the name scares people off.
It really does. But the goal of this deep dive isn't just to recite facts at you. We are going to walk through our source material chapter by chapter, decoding the specific academic language.
And the laboratory pragmatism, too, plus the theoretical physics.
Right, so that by the end of our time today, you will have the framework to pick up literally any advanced chemistry or physics textbook and parse it with total ease.
We are essentially building a skeleton key for nuclear literature.
So what's the blueprint for that skeleton key today?
The source material is the second edition of a highly specific text titled Nuclear Chemistry. It's authored by Maheshwar Sharon and Madhuri Sharon.
And the motivation behind this book is really what makes it so valuable for our purposes, right?
Oh, absolutely. The authors, through their own teaching and research, they basically identified this critical gap in how students and professionals were approaching radioactive tracer techniques.
Like, people were stepping into laboratories armed with a theoretical understanding of decay equations.
Yeah, they knew the math on paper, but they were completely lost when it came to the practical, physical execution of an experiment.
They lacked the intuition for it.
Exactly. They didn't know how to select the appropriate isotope for a specific chemical pathway. They didn't understand the physical limitations of their counting instruments. And they were frequently just compromising their own data through really poor sample preparation.
Which is a nightmare when you're dealing with invisible radiation. So the authors wrote this text explicitly to bridge that gap between quantum theory and laboratory reality.
It is a guide to the why and the how of measuring the invisible.
To properly set the stage for that intersection of theory and reality, I think we really should look at how the authors open the book.
The dedication, it's fascinating.
It really is. They include a dedication that completely challenges the conventional Western timeline of atomic discovery. I mean, usually the concept of the atom is inextricably linked to John Dalton.
Right. Early 19th century Europe, the standard historical narrative always treats the atom as this product of the European Enlightenment and the Industrial Revolution.
But this text dedicates its pages to a figure who predates Dalton by a staggering margin. It shifts the origin point of atomic theory entirely to ancient India.
The dedication is to Acharya Kanad. He's the foundational philosopher of the Vaisheshik Darshan, which is recognized as one of the 6 principal orthodox philosophies of ancient India.
And the chronological gap here is just immense.
It's massive. Kanad lived and formalized his theories nearly 2,500 years before Dalton published his atomic theory.
Yet Kanad is presented in this text as the pioneer expounder of structural atomism.
Right, he didn't just propose that matter was divisible. He created this highly formalized, categorized system of the universe's building blocks.
The specifics of his classification system are so fascinating to me because they blend these metaphysical concepts with a really prescient physical framework.
Yeah, he divided all objects of creation into 9 foundational elements.
You have the familiar physical categories, right? Earth, water, light, wind, and ether.
But he also included time, space, mind, and soul as fundamental elements.
And while modern physics obviously separates the metaphysical mind and soul from the standard model of particle physics, his treatment of the physical elements is what is so striking.
Because he explicitly argued that every physical object of creation is composed of indivisible spherical particles, atoms.
And he didn't stop there. He posited that these atoms do not just exist in isolation. They actively combine and connect with one another to form what we would now call molecules.
The conceptual leap there is just profound, going from observing macroscopic matter to theorizing microscopic combinatorial atoms without any instrumental aid, no microscopes, no colliders.
Just rigorous logical deduction. He even detailed the dimensions of these particles, theorized about their inherent motion, and described the fundamental nature of their chemical reactions when they combine or separate.
There's actually a prominent historian cited in the book, T.N. Colebrook, who notes that compared to the scientific development in Europe during Antiquity, Kanad and his contemporaries were operating at a level of theoretical physics that was globally unmatched.
They were conceptualizing the mechanics of atomic motion purely through philosophical inquiry.
So the inclusion of Kanad at the very beginning of a modern textbook on nuclear chemistry serves a very specific rhetorical purpose for you, the listener.
Exactly. If a philosopher operating 2.5 millennia ago could conceptualize the structural mechanics of molecules using nothing but observation and logic, the dense material we're about to cover is entirely within your grasp.
We have the benefit of centuries of empirical data, particle accelerators, and quantum mechanics to back up the theory now.
So, utilizing that advantage, let's dive directly into segment 1, inside the nucleus. Chapter 1 requires us to completely deconstruct the atom.
Right. When we approach general chemistry, the focus is almost entirely on the electron orbitals.
Chemical bonds, oxidation states, reactivity.
All of that is just a function of the electron cloud interacting with other electron clouds.
But nuclear chemistry demands that we strip away the orbitals entirely. We don't care about the electrons right now.
We are focusing on the incredibly dense central core of the atom, which houses the protons and neutrons, the nucleons.
And the text introduces the internal architecture of this core through the shell model.
Which is a big step up from the classical visualization. A lot of people still picture the liquid drop model, where protons and neutrons are just densely packed together in this homogeneous, vibrating sphere, kind of behaving like molecules in a drop of water.
But the shell model introduces rigorous quantum mechanical organization to the nucleus.
It applies the exact same quantum logic we use for electrons to the nucleons themselves.
Right, just as electrons cannot exist in arbitrary spaces around the nucleus and are confined to specific discrete energy levels.
Protons and neutrons are confined to specific, discrete energy levels inside the potential well of the nucleus.
They fill these nuclear shells in a strict mathematical hierarchy. Because protons and neutrons are fermions, right?
Exactly. They obey the Pauli exclusion principle. No two identical nucleons can occupy the exact same quantum states simultaneously.
And that requirement for unique quantum states drives the entire structure of the shell model.
As you add nucleons to a nucleus, they fill the lowest available energy states first. But here's the trick. Protons and neutrons are different particles, so they actually operate in two separate parallel shell systems within the same nucleus.
You have one set of energy levels filling up with protons and another separate set filling up with neutrons.
And just like the noble gases in standard chemistry, where a completely full electron shell gives you a highly stable, unreactive element like helium or neon.
A completely full nuclear shell results in an exceptionally stable nucleus.
And the specific numbers of nucleons required to perfectly fill these major energy shells are known in the literature as magic numbers.
Magic numbers. I love that physicists use terms like that. The numbers are 2, 8, 20, 28, 50, 82, and 126.
They are empirical realities that the shell model elegantly explains. When a nucleus possesses a magic number of either protons or neutrons, its binding energy per nucleon spikes.
Meaning it is tightly bound and highly resistant to decay.
Right. And if a nucleus has a magic number of both protons and neutrons, it is considered doubly magic and is incredibly stable.
The text actually uses the naturally occurring radioactive decay series to illustrate how these magic numbers manifest physically in nature.
The uranium-238 decay series is the perfect case study for this.
Uranium-238 is an unstable, heavy isotope. It does not possess a magic number of protons or neutrons, so it sits in this state of high potential energy.
It's agitated. To relieve that energy, it undergoes a protracted sequential series of radioactive decays. It emits an alpha particle to become thorium-234.
Which beta decays into protactinium-234.
Which beta decays into uranium-234, and so on. It cascades down the periodic table, throwing off mass and energy.
But this chaotic chain of transmutations isn't infinite. It invariably terminates at a very specific endpoint.
Lead-206.
And lead-206 is completely stable. It does not decay further.
Because the shell model provides the exact reason why. Lead has an atomic number of 82. That is a magic number of protons.
And the lead-206 also contains 124 neutrons, which is very close to the magic number of 126.
The entire sequence of radioactivity is essentially the thermodynamic drive of the nucleus to shed excess mass and energy until it achieves that tightly bound, highly stable configuration associated with the magic numbers.
Which brings us perfectly to Chapter 2, the dynamics of decay. because this thermodynamic drive to reach a stable quantum state is the underlying mechanism of all radioactivity.
Radioactivity is just the observable symptom of an unstable nuclear configuration.
The nucleus is attempting to optimize its proton-to-neutron ratio. It achieves this by emitting particulate radiation.
Like heavy, positively charged alpha particles, which reduce both proton and neutron counts.
Or beta particles, which involve the internal conversion of a neutron into a proton, or vice versa, and ejecting an electron or positron.
Or, if the nucleus is just in an excited, energetic state without needing to alter its mass or charge, it will emit electromagnetic radiation in the form of high-energy gamma rays.
But the mathematical tracking of these emissions is where the real practical application of nuclear chemistry begins.
The text places huge emphasis on the concept of parent-daughter equilibrium. It's a vital tool for quantitative analysis in the laboratory.
When a parent isotope undergoes radioactive decay, it transforms into a daughter isotope. But crucially, in many decay chains, the daughter isotope is itself radioactive.
Right, and it will subsequently decay into a granddaughter isotope. This creates a coupled differential system. The daughter is simultaneously being produced by the parent and depleted by its own decay.
It's like filling a bucket with a hole in the bottom. Over time, depending on the relative half-lives of the parent and the daughter, the rates of production and decay can synchronize.
They establish a state of equilibrium.
The specific examples provided in the source highlight how different half-life ratios dictate the type of equilibrium achieved, like the relationship between barium-140 and lanthanum-140.
That's a classic example of transient equilibrium. Barium-140 is the parent. It has a half-life of 12.8 days. It decays by emitting a beta particle to become lanthanum-140.
And lanthanum-140, the daughter, has a much shorter half-life of approximately 40 hours.
So if you isolate a pure sample of freshly separated barium-140, the initial activity of lanthanum-140 is 0.
But as the barium begins to decay, the lanthanum activity rapidly grows.
Because the lanthanum is decaying much faster than the barium, it eventually reaches a point where its rate of decay exactly matches its rate of production from the barium.
At this point, the ratio of the activity of the parent to the activity of the daughter becomes constant. Both effectively appear to decay at the slower rate of the parent.
The text also references the decay of polonium-218 down to lead-214. That's a segment of the larger uranium-222 decay chain.
Polonium-218 has a half-life of just over 3 minutes, decaying via alpha emission to lead-214, which has a half-life of about 27 minutes.
The mathematical predictability of these coupled decay curves is a tremendous asset for you if you're a radiochemist. If you know that a system has reached equilibrium, you no longer need to measure both isotopes.
You can accurately infer the concentration and activity of the parent by solely measuring the emissions of the daughter, or vice versa.
This mathematical synchronization turns the seemingly chaotic, random decay of individual atoms into a highly predictable, reliable macroscopic clock.
It allows researchers to quantify elements in complex mixtures, where direct measurement of one component might be technically difficult or even physically impossible due to interference.
Which leads us into Segment 2, The Art of Detection, Chapters 3, 5, 6, and 7 of the source material. We transition from the theoretical behavior of the nucleus to the highly specialized art of catching the invisible.
The fundamental problem in trace analytical chemistry is identifying elements present at concentrations so low.
We're talking nanogram or picogram levels.
Right, levels where standard chemical titration, spectroscopy, or gravimetric analysis completely fail. You just can't see them.
So Chapter 3 introduces the methodology of deliberately inducing radioactivity through nuclear reactions.
If we have incredibly minute, stable, silent traces of an element hidden in a larger matrix, the radiochemical solution is to force those stable isotopes to reveal themselves.
You deliberately bombard the sample with subatomic particles. The most common method utilizes thermal neutrons generated in a nuclear reactor.
Because neutrons carry no electrical charge, they aren't repelled by the positively charged nucleus. They just drift right in and are absorbed via the strong nuclear force.
And when a stable isotope captures a neutron, its mass increases by 1 atomic mass unit, but its atomic number remains the same. This frequently creates a neutron-rich, highly unstable isotope.
The previously stable, undetectable element has now been converted into a radioactive emitter. We've energetically tagged it.
Once this induced radioactivity begins, the newly formed unstable isotopes undergo decay, emitting characteristic beta particles and gamma rays.
Because the decay scheme of every radioactive isotope is unique and well documented, measuring the specific energies and half-lives of this induced radiation allows us to definitively identify the original stable element,
And by knowing the flux of the neutrons used for bombardment and the nuclear cross-section.
which is basically the probability of that specific isotope capturing a neutron.
Right, the researcher can mathematically calculate the exact mass of the trace element originally present in the sample.
But identifying the radiation conceptually is one thing. Practically, it requires sophisticated instrumentation. How do we actually catch these rays?
Chapter 5 focuses on the fundamental architecture of the ionization counter, specifically the Geiger-Müller or GM counter.
The classic clicking box you see in movies.
Exactly. The mechanism relies on the interaction between high-energy particulate radiation and a noble gas. The counter consists of a sealed chamber filled with a gas, typically argon, at low pressure.
A high voltage potential is applied across the chamber, with a central wire acting as the anode and the outer wall acting as the cathode.
When ionizing radiation, like an alpha or beta particle, enters this chamber, its kinetic energy is transferred to the argon atoms.
And that transferred energy is sufficient to overcome the binding energy of the argon's valence electrons.
The passing radiation essentially shears an electron right out of the argon atom's outermost shell. This creates an ion pair, a free, negatively charged electron and a heavy, positively charged argon ion.
Because of that high voltage applied across the chamber, the free electron is immediately accelerated toward the central anode wire.
As it accelerates, it gains enough kinetic energy to ionize subsequent argon atoms in its path, which in turn release more electrons.
It creates a massive cascading effect, a Townsend avalanche. Millions of electrons hit the central wire almost simultaneously, producing a measurable electrical pulse.
Every single pulse recorded by the electronics corresponds to a single incident particle of radiation entering the chamber.
It's a robust design, but the authors emphasize some severe practical limitations and experimental errors that can arise if the physical properties of the sample aren't rigorously controlled.
A prime example they give is the density issue encountered when using liquid GM counters.
These are specialized counters where a glass jacket surrounds the central counting tube, allowing a radioactive liquid sample to be poured directly around the detector for maximum efficiency.
But here's the trap. Imagine measuring the exact same absolute quantity of a radioactive isotope dissolved in two distinct liquids with significantly different densities.
Say you're studying an isotope moving between an aqueous phase, like water, and a dense organic phase, like chloroform.
If you extract exactly 10 milliliters of the water phase containing X amount of radioactivity, and you extract exactly 10 milliliters of the dense chloroform phase containing the exact same X amount,
Well, logic tells you the counter will register the exact same activity rate for both. They are identical volumes containing identical amounts of the emitter.
but the empirical data plotted in the text shows that as the specific gravity of the liquid solvent increases, the measured count rate actively decreases.
It's so counterintuitive.
It's caused by the physical interaction between the emitted radiation and the electron density of the solvent itself. A denser liquid contains more atoms and therefore a higher electron density per unit volume.
As the beta particles are emitted by the isotope suspended in the dense liquid, they have a much higher probability of colliding with the solvent molecules before they can traverse the fluid and enter the counting chamber.
The denser liquid is effectively acting as a highly efficient internal shield, absorbing a significant fraction of its own radiation.
If you don't recognize this phenomenon, you'll incorrectly conclude that the dense organic phase contains less of the radioactive isotope.
To correct for this internal shielding, the radiochemist has to generate a fractional loss calculation.
They prepare a series of standard solutions containing a known constant amount of radioactivity dissolved in a gradient of varying densities.
By counting each standard and plotting the observed activity against the specific gravity of the solvent, they establish a definitive mathematical curve of efficiency loss.
So when you analyze an unknown sample, you measure its specific gravity, locate that value on your curve, and apply the corresponding correction factor to the observed count rate.
That mathematical normalization ensures the final calculated activity represents the true absolute amount of the isotope, regardless of the solvent's physical density.
But this rigorous mathematical correction also highlights the limitations of the ionization counter. Chapter 6 points out a fundamental flaw. GM counters are highly efficient for charged particles like alpha and beta, but they are incredibly inefficient for gamma rays.
They often detect less than 1% of incident gamma rays. Because gamma rays are uncharged electromagnetic photons, lacking a charge, they interact very weakly with matter.
A gamma photon will typically pass straight through that low-density argon gas without ever striking an electron to initiate an avalanche.
To efficiently detect gamma radiation, you have to shift from ionizing a gas to exciting a solid crystal. You need the scintillation counter.
The operational principle here relies on the photoelectric effect and Compton, scattering within a highly dense crystalline matrix. Instead of a gas chamber, the radiation hits a phosphor.
For gamma-ray spectroscopy, the industry-standard phosphor discussed in the text is a single crystal of sodium iodide that's been intentionally doped with a trace amount of thallium, NaITL.
The high physical density and high atomic number of the iodine atoms drastically increase the probability that a gamma photon will interact with the crystal lattice.
When a gamma ray strikes the crystal, it transfers its energy to the electrons within the lattice. These excited electrons migrate through the crystal until they encounter the thallium impurity centers.
The thallium lowers the energy band gap. As the electrons de-excite and return to their ground state at these centers, they release the absorbed energy in the form of a visible photon.
A tiny flash of light, a scintillation. The brilliance of this system is that the intensity of the light flash is directly proportional to the energy of the incident gamma ray.
But that microscopic flash of light is far too faint to be measured directly. The crystal has to be optically coupled to a photomultiplier tube.
The photomultiplier tube is an ingenious piece of vacuum electronics. The light photon emitted from the crystal strikes the photocathode at the front of the tube, ejecting a single primary electron via the photoelectric effect.
This single electron is then accelerated by a high voltage potential into a series of positively charged electrodes called dinodes.
When the primary electron strikes the first dynode, it knocks loose several secondary electrons,
which are accelerated into the second dynode, where they each knock loose several more.
This cascading amplification across multiple dinodes results in an avalanche of millions of electrons reaching the final anode, creating a robust, measurable electrical current pulse from a single initial flash of light.
It's brilliant engineering. But just as the GM counter is vulnerable to density, the scintillation counter is highly susceptible to an experimental artifact known as quenching.
Especially when using liquid scintillation counting, where the radioactive sample is dissolved directly into a liquid organic phosphor cocktail to measure low-energy beta emitters like tritium or carbon-14.
The chemical composition of the sample matrix itself becomes a massive variable. Chemical quenching occurs when non-radioactive impurities in the sample interfere with the energy transfer process.
These impurities, often polar solvents or dissolved oxygen, essentially absorb the excitation energy from the solvent molecules non-radiatively. They dissipate it as microscopic thermal heat before it can ever reach the primary floor to create a photon of light.
Then there is color quenching, which happens when the sample itself is physically pigmented.
Even if the excitation energy successfully reaches the floor and a photon of light is emitted, a deeply colored sample matrix acts like a physical filter, absorbing the emitted light photon before it can escape the vial.
In both chemical and color quenching, the radioactive decay occurs. The energy is deposited, but the photomultiplier tube sees nothing. The observed count rate artificially plummets.
And physically removing these quenching agents without altering the radioactive isotope is often chemically impossible. So, the text outlines a mathematical workaround utilizing a quench correction curve.
You prepare a set of sealed, standardized vials, all containing the exact same highly calibrated amount of radioactivity.
To each successive vial, an increasing measured volume of a known quenching agent is added. You count the vials and calculate the counting efficiency of each relative to the unquenched standard.
This generates a definitive, plottable curve correlating the percentage of efficiency lost directly to a specific quench parameter.
You analyze an unknown sample, determine its quench parameter located on the curve, and mathematically restore the artificially depressed count rate back to the true absolute activity.
Which brings us to Chapter 7 and the evolution to solid-state precision with semiconductor detectors. High-purity silicon or germanium crystals represent the modern standard for ultra-high-resolution spectroscopy.
They're used for differentiating complex mixtures of low-energy particles and soft X-rays. And to explain how these solid-state devices operate, the text delves into band gap theory.
The authors use this highly memorable macroscopic analogy to illustrate a complex quantum mechanical perturbation. It's fantastic.
It really is. They use it to visualize how atomic proximity alters electronic states. When an atom exists in a vacuum, completely isolated, its electrons occupy discrete, sharply defined atomic orbitals.
The electrons are in a state of unperturbed equilibrium, influenced only by the electrostatic pull of their own nucleus.
The authors analogize this isolated ground state atom to a person sitting completely alone in a quiet room, peacefully reading a book.
You are in a state of relaxed equilibrium. Your energy level is stable.
But a semiconductor crystal is not a vacuum. It is a dense, rigid lattice where billions of atoms are forced into incredibly close physical proximity.
The outer valence electrons of any given atom are no longer solely influenced by their own parent nucleus. They are subjected to the strong electrostatic forces of the neighboring atomic nuclei surrounding them.
The equilibrium of the isolated atom is completely shattered. And the author's analogy for this perturbation is striking. Imagine you are that person peacefully reading a book, and suddenly, a very beautiful girl enters the room and stands immediately next to you.
The physical presence of this new, highly charged variable in your immediate vicinity irrevocably alters your state. You can no longer maintain your relaxed equilibrium.
You physiologically react. Your heart rate increases. You sit up straighter. Your focus shifts. Your energy level has been fundamentally perturbed.
And the authors argue that if a macroscopic human system alters its energy state due to the close physical proximity of a disrupting variable, the quantum system of an electron must do the same.
Because of the overwhelming electrostatic influence of the neighboring atoms in the crystal lattice, the outer electrons can no longer remain in their single, sharply defined energy orbital.
The Pauli exclusion principle forbids all these overlapping electrons from occupying the exact same energy state.
Consequently, the single discrete energy level of the isolated atom is forced to split and broaden into two entirely distinct energy bands.
The lower energy band, where the electrons are normally bound to the lattice structure, is the valence band.
The higher energy band, where electrons are free to migrate through the crystal and conduct electricity, is the conduction band.
And the physical space between these two bands, the range of forbidden energy levels where no electron can exist, is the band gap.
The exact amount of kinetic energy an electron must absorb to jump the band gap is dictated entirely by the specific elemental composition and the tightness of the crystal lattice.
In a semiconductor detector, this band gap is meticulously engineered. When incident ionizing radiation enters the crystal, it collides with an electron in the valence band, transferring a very specific quantum of kinetic energy.
If this energy bridges the band gap, the electron is promoted into the conduction band, leaving behind a positively charged hole in the valence band.
Under an applied bias voltage, these electron-hole pairs migrate toward opposite electrodes, generating a highly precise electrical pulse.
And because the energy required to create an electron-hole pair in germanium is incredibly small compared to the ionization energy of argon gas, the semiconductor detector can resolve minute differences in radiation energy with vastly superior precision.
But understanding the physics of these detectors is only half the battle. The detector is only as reliable as the sample placed in front of it. This brings us to segment 3, Perfecting the Setup, chapters 8 and 9.
These chapters are dedicated to the rigorous, often tedious procedures of sample preparation and the geometric and physical factors that can completely invalidate experimental data.
The overarching theme here is that radiochemistry is highly sensitive to physical geometry. You can't just take an unrefined environmental sample, like a piece of radioactive ore, place it in front of a window, and expect a valid reading.
The physical state of the source material profoundly influences the measured count rate. Solid samples often have to be chemically digested, precipitated, dried, ground into an exceptionally fine powder,
And then uniformly suspended using specialized gelling agents to ensure the geometry relative to the detector remains perfectly constant.
The necessity for this extreme rigor is driven by a phenomenon the book details as the illusion of thickness, self-absorption.
It is highly counterintuitive and frequently confounds novice researchers. The authors construct a theoretical experiment to prove it, using a radioactive precipitate of barium sulfate, labeled with sulfur-35, a pure beta emitter.
The experimental design involves taking a series of identical counting dishes, planchettes. You sequentially pipette increasing volumes of the identical radioactive suspension into the planchettes.
Planchet 1 gets 1 milliliter, planchet 2 gets 2 milliliters, up to planchet 10, which gets 10 milliliters.
Mathematically, the specific activity, the concentration of radioactive atoms per unit volume, is identical across all aliquots.
Planchet 10 physically contains exactly 10 times the mass of the precipitate, and therefore exactly 10 times the absolute quantity of sulfur-35 atoms.
So the logical assumption is that when these planchets are counted, the observed rate will plot as a perfectly linear proportional increase.
1 unit of mass yields 1 unit of counts, 10 units yields 10 units.
But the empirical reality heavily deviates from this. The resulting graph initially shows a near-linear increase for the first few very thin planchets.
But rapidly, the curve begins to roll over, deviating from linearity and rising exponentially slower. Eventually, the curve completely flattens out into a horizontal plateau.
Planchet 8, 9, and 10 might all register the exact same absolute count rate on the detector, even though planchet 10 contains significantly more sulfur-35.
The extra radiation being emitted by the larger mass is seemingly vanishing. This plateau is saturation thickness, or infinite thickness.
The radiation isn't defying physics, it's being consumed by the physics of the sample matrix itself.
To understand the mechanism, imagine dividing the solid sample in the planchet into thousands of infinitely thin horizontal planes stacked on top of each other.
The beta particles emitted by the atoms in the uppermost plane, right at the surface, face almost no physical resistance. They exit immediately and enter the detector window with near maximum efficiency.
But the atoms in the internal planes have a completely different dynamic. A beta particle emitted from the middle of the sample must first traverse the upper physical layers of the dense barium sulfate before it can reach the air gap.
As it interacts with the dense electron clouds along its path, it undergoes multiple scattering events and loses kinetic energy.
If the sample is sufficiently thick, the beta particle will lose all of its kinetic energy and be completely absorbed by the upper layers of its own chemical matrix before it can ever escape.
So as you add more radioactive sustention, you are increasing the vertical depth. Once that physical depth exceeds the maximum range of the beta particle, any additional material added to the bottom becomes completely irrelevant to the detector.
The beta particles from those bottom layers are entirely absorbed by the layers sitting above them. The sample has reached saturation thickness. It's effectively acting as its own internal lead shield.
The detector only registers the decay events occurring in the uppermost unshielded active layer, which remains constant in thickness regardless of how much material is beneath it.
This presents a massive experimental crisis.
Yeah.
If a student is analyzing samples that vary naturally in total precipitated mass, and they don't know about self-absorption, their comparative data is totally invalid.
The standard hack to resolve this relies on mathematically sound pragmatism. The radiochemist calculates the specific saturation thickness for the density of their precipitate.
Then, they deliberately add a carefully measured mass of an inert, non-radioactive carrier compound, like stable barium sulfate, to every single sample.
You artificially bulk up the physical mass of every sample to ensure that every single planchet significantly exceeds the threshold for saturation thickness.
Yes, the overall gross count rate drops significantly because the specific activity of the surface layer is diluted.
But the critical advantage is that the count rate becomes completely uniform and totally independent of the sample's total physical thickness.
Because every sample is counting at infinite thickness, the self-absorption variable is standardized. You're comparing standardized surface emissions.
Once you master those physical variables, chapters 9 and 10 address qualitative analysis, identifying an unknown isotope using fundamental physical principles.
The source uses cesium-137 as a primary example. It's a widely utilized, long-lived fission product. It decays primarily by emitting a relatively low-energy beta particle.
But its daughter product, barium-137 meter, rapidly transitions to its stable ground state by emitting a highly energetic gamma ray in 94% of all decay events.
So cesium-137 is effectively a prolific gamma emitter.
And because of that, highly sensitive sample prep isn't always required for gross detection. A standard GM counter is fine if you just want to confirm its presence.
But qualitative identification, proving definitively that it's cesium-137 and not cobalt-60 or iodine-131, requires measuring the exact kinetic energy of those gamma rays.
If you don't have a sophisticated semiconductor multi-channel analyzer, you can use a purely physical technique known as half-thickness measurement.
The concept of half-thickness is the spatial geometric equivalent of the temporal half-life.
While half-life defines the time required for the disintegration rate to decrease by 50%, Half thickness defines the physical thickness of a solid absorber required to attenuate the intensity of the radiation beam by exactly 50%.
The underlying physics is based on the exponential attenuation of electromagnetic radiation as it interacts with matter, the same mathematical principles as the Beer-Lambert law.
The intensity of the transmitted radiation decreases exponentially, according to the formula I equals I, 0 times e to the negative mu x.
I is the final transmitted intensity, I0 is the initial unshielded intensity, x is the physical thickness of the absorber, and mu is the linear absorption coefficient.
That linear absorption coefficient is a highly specific, energy-dependent constant. It defines the exact probability of a gamma photon interacting with the atomic lattice of the absorbing material.
By setting the final intensity I to exactly 1/2 the initial intensity, the equation simplifies to x 0.5 equals 0.693 divided by mu.
This relationship is the skeleton key for qualitative identification. Every single radioactive isotope possesses a unique, highly specific half-thickness value for a given absorbing material.
The experimental execution is brilliant. You place the unknown sample in front of a detector, record the unshielded count rate.
Then you systematically insert precision machine sheets of high-purity lead between the source and the detector, incrementally increasing the thickness.
You record the attenuated count rate at each interval, plot it on a semi-logarithmic graph, and generate a straight-line attenuation curve.
You locate the point on the axis that corresponds to exactly 50% of the initial count rate, trace horizontally to the curve, and drop down to the x-axis to read the exact physical thickness of the lead.
If that value is, say, exactly 6.5 millimeters of lead, you check a standardized table.
And the table confirms that a half-thickness of 6.5 millimeters of lead correlates precisely to a gamma-ray energy of 0.662 memen.
That signature belongs exclusively to the barium-137-meter daughter of cesium-137. You've definitively identified the invisible isotope using basic counters, lead plates, and physical math.
Moving from physical predictability to inherent instability, Segment 4 dives into Chapters 11 and 12. The rigorous statistics required to manage the chaotic reality of radioactive data and the biological consequences of that radiation.
Chapter 11 emphasizes a fundamental truth of quantum mechanics. Radioactive decay is an entirely random, stochastic process at the level of the individual atom.
It is physically impossible to predict exactly when any specific unstable nucleus will disintegrate.
The text illustrates this using carbon-14, which has a half-life of over 5,700 years. Its average decay rate over a single day is practically constant.
But if you place a sample under a proportional counter and record the disintegrations over exactly 1 minute, you might get 9,650 counts.
If you leave it absolutely undisturbed and recount it for a second identical minute, the detector might register 10,059 counts.
The sample hasn't changed, the geometry is identical, yet the data fluctuates widely by hundreds of counts.
It's the manifestation of the Poisson distribution governing the random quantum decay.
This introduces a fundamental statistical dilemma. Is it mathematically superior to conduct one single extended count, like 60 minutes, or 20 short 3-minute counts, and average them?
The intuitive approach taught in basic science is to calculate the arithmetic mean. We're conditioned to believe averages smooth out variance.
But the authors employ a stark, memorable analogy to violently shake the reader out of this false sense of security, the river crossing analogy.
A family of 5 wants to cross a river on foot. The leader wades across first to map the topography, measuring the depth at equidistant intervals.
They compile the measurements and calculate that the arithmetic average depth of the river is exactly 90 centimeters.
The leader evaluates the shortest member of the family, a child who is 105 centimeters tall.
The leader applies basic logic. Average depth is 90, child is 105. There's a 15-centimeter clearance. The family can safely cross.
They proceed into the water, and everyone except the leader drowns in the middle of the river.
Because the arithmetic average calculation completely smoothed over and mathematically erased the physical extremes of the riverbed.
The shallow shoals near the banks dragged the overall average down, but the physical reality included a deep central trench that was 150 centimeters deep.
The calculated average of 90 centimeters was mathematically correct, but it completely failed to account for the maximum standard deviations, the deep trenches that represented fatal extremes.
By blindly trusting the smooth average without defining the boundaries of the variance, the leader led the family into a lethal environment.
Connecting this back to carbon-14 counts, the lesson is that merely calculating the arithmetic average is mathematically insufficient and dangerous.
Calculating the arithmetic mean must be accompanied by the calculation of the standard deviation and the variance of the dataset.
The standard deviation mathematically defines the deep trenches. It establishes the specific boundaries and margins of error surrounding the calculated average, defining the statistical confidence interval.
Relying on an average without calculating the standard deviation means you do not understand the true physical reality of the chaotic decay data. You're operating blind to the extremes.
And the necessity of accurately mapping those extremes is underscored by the physical consequences detailed in Chapter 12. Health hazards.
The physical interaction of high-energy radiation with complex biological tissue is profoundly destructive. The text categorizes the damage into two distinct pathological pathways.
Based on exactly which cellular component absorbs the kinetic energy, the first pathway is cytoplasmic damage.
The cytoplasm is the highly complex, aqueous, jelly-like matrix filling the interior volume of the cell.
When ionizing radiation traverses the cytoplasm, its primary interaction is the ionization of water molecules, a process known as radiolysis.
This intense ionization generates highly reactive, volatile free radicals like the hydroxyl radical.
These free radicals are chemically aggressive. They rapidly attack the lipid membranes and enzymatic proteins suspended in the cytoplasm, causing severe localized oxidative stress and metabolic disruption.
However, the text notes that cytoplasmic damage, while traumatic, is often somatic and theoretically recoverable.
The biological cell has a robust defense mechanism of antioxidant enzymes designed to neutralize reactive oxygen species.
As long as the rate of radiation-induced free radical generation is significantly slower than the body's natural enzymatic rate of cellular recovery, the system can manage the oxidative stress.
The second pathway, however, represents the true nightmare scenario: nucleus damage.
If the radiation penetrates through the cytoplasm and strikes the dense central nucleus, the vault containing the DNA, the damage is fundamentally different.
The kinetic energy can physically strike the DNA double helix directly, or the localized free radicals can chemically attack the nucleic acids.
This interaction causes severe physical disruption to the 23 pairs of human chromosomes. The radiation literally shatters the structural integrity of the genetic code.
It causes single-strand breaks, which might be repaired, or far more lethally, double-strand breaks, where the entire physical backbone of the DNA molecule is severed.
When the genetic code is physically snipped and fragmented, it leads to permanent, inheritable genetic mutations.
The cell's repair mechanisms frequently fail to correctly reassemble the shattered sequences, resulting in massive deletions or translocations.
The foundational biological blueprint is corrupted. The text notes these localized chromosomal aberrations can manifest as observable altered characteristics, like sudden, unexplainable changes in pigmentation, localized cell death, or severe hair loss.
Far more dangerously, the mutations can disable the specific regulatory genes responsible for controlling cellular division and apoptosis.
When these regulatory mechanisms are destroyed, the cell enters a state of aggressive, uncontrolled rapid replication, runaway cellular mutation.
Which is the fundamental mechanism of radiation-induced malignancy and cancer. The physical power of the radiation alters the fundamental biological instructions of life.
The immense biological hazard posed by microscopic quantities of radioactive material underscores the extreme necessity for absolute chemical and radiochemical purity in the laboratory.
Which transitions us into our final and most complex segment, Segment 5, Advanced Wizardry, Chapters 13 and 14.
Where theoretical mechanics and pragmatic execution converge. Chapter 13 focuses on radiochemical separation.
Once a target has been bombarded with neutrons to induce radioactivity, the resulting sample is a highly complex radioactive soup. It contains the newly synthesized target isotope, massive quantities of unreactive parent isotope, and trace activation products.
The challenge is isolating the single desired radioactive isotope from this chaotic matrix.
And the text establishes the foundational golden rule of radiochemistry. Purity is defined at the atomic level, not the macroscopic level.
In standard organic chemistry, if you isolate a compound at 99% chemical purity, it's a massive success. The remaining 1% won't invalidate the data.
But in radiochemistry, a chemical impurity is fundamentally distinct from a radioactive impurity, and the tolerance for the latter is effectively zero.
The text explicitly drives this home. It argues mathematically that it is vastly superior to have a sample contaminated with several milligrams of a heavy, inert, non-radioactive chemical impurity.
Like stable lead or stable calcium?
Right, than it is to have a sample contaminated with 10 to the negative ninth grams of an active high-energy radioactive impurity.
A single billionth of a gram. The reasoning is based on the sensitivity of the equipment. A few milligrams of stable calcium sits silently. It emits no energy, triggers no ion pairs, flashes no photons.
But 1 billionth of a gram of a highly active, uninvited radioactive isotope like cobalt-60 will violently and continuously fire highly energetic gamma rays into the detector.
It completely overwhelms the counting electronics, burying the faint signal of the target isotope under a wave of false data, utterly invalidating the experiment.
To achieve this atomic level of specific isolation, the text details advanced separation techniques like paper chromatography.
Which relies on the differential partition coefficients of radioactive ions moving between a stationary cellulose phase and a mobile solvent phase.
You spot a precise microdrop of the soup onto filter paper, suspend it in a sealed tank with a solvent, and capillary action wicks the solvent up.
Different isotopic complexes have different affinities, so they migrate at varying speeds, separating into distinct invisible bands characterized by specific retention factors.
The dried paper is then physically scanned with a collimated GM tube or exposed to sensitive X-ray film to visually map the exact location of the separated isotopes.
But the text highlights a far more intense, mechanically rigorous example utilizing ion exchange chromatography, the historic experiment by Gregory Chopin to separate transuranic elements from lanthanide elements like samarium.
Super heavy synthetic elements. This separation is notoriously difficult because they share nearly identical chemical properties and oxidation states.
Chopin's experimental architecture required intense physical and thermodynamic control. The physical setup utilized a vertical glass column packed with a specific synthetic cation exchanger resin called DOX50.
The resin contains negatively charged sulfonate groups that aggressively bind the positively charged transuranic and lanthanide ions.
The critical variable was extreme thermodynamic stability. The complexation reactions inside the column were highly sensitive to minute temperature fluctuations.
To maintain the column at an absolute unwavering 80 degrees Celsius, Chopin didn't use standard electrical heating tape.
He enclosed the entire vertical ion exchange column within an outer glass jacket and continuously circulated the vaporized steam of boiling trichloroethylene through the jacket.
Trichloroethylene is an organic solvent with a precise physical boiling point of exactly 80 degrees Celsius at standard atmospheric pressure.
By utilizing the phase change thermodynamics of the boiling solvent, he enveloped the column in a perfectly calibrated, self-regulating steam bath that physically could not exceed or drop below the target temperature.
Once stabilized, an ammonium lactate eluent solution was poured into the top. As it percolated down through the heated DOX50 resin, it engaged in a fierce competition with the resin's sulfonate groups for the bound metal ions.
The binding affinity depends on the exact ionic radius. Because of the actinide contraction, the heaviest elements form slightly stronger, tighter complexes with the eluent.
So these heaviest elements are stripped away from the resin first. As the liquid dripped out of the bottom nozzle, Chopin's team collected every single individual drop separately on individual planchettes.
They evaporated the solvent, created hundreds of individual counting sources, and meticulously measured the alpha activity of each drop.
And when they plotted the specific activity against the volume of the eluent passed, the elution curve reveals something truly remarkable.
The elements emerged in exact, sequential reverse order of their atomic numbers.
The heaviest transuranic element, with the smallest ionic radius, eluted first in a sharp concentrated band, followed exactly by the next heaviest, terminating with a lighter samarium.
By manipulating complexation thermodynamics and phase change temperature control, they achieved perfect atom-by-atom isolation of super-heavy elements.
The application of nuclear technology for precise elemental identification is further expanded through activation analysis.
This is an incredibly brilliant, non-destructive analytical method used when you have a highly precious, completely irreplaceable sample.
Like ancient, priceless archaeological artifacts or highly sensitive forensic evidence. You can't dissolve an ancient coin in nitric acid to test it.
Activation analysis bypasses physical destruction entirely. You place the intact solid artifact directly into the high neutron flux core of a nuclear research reactor.
The artifact is blasted with a massive storm of thermal neutrons. The neutrons effortlessly penetrate the physical matrix without altering its macroscopic structure.
As the neutrons interact with microscopic trace elemental impurities hidden inside, those stable isotopes capture the neutrons and transmute into highly unstable radioactive isotopes.
You retrieve the intact artifact. It is now emitting radiation, because every newly synthesized radioactive isotope decays by emitting gamma rays with highly specific signature kinetic energies.
You simply place the intact, emitting artifact in front of a high-resolution germanium semiconductor detector.
By analyzing the precise energy spectrum of the emitted gamma rays, you can definitively identify every single trace element hidden within the artifact's matrix.
And by measuring the intensity, you calculate the exact concentration down to the part per billion level. You map the internal atomic composition by listening to the quantum echoes, all while the physical artifact remains completely untouched.
This non-destructive probing relies on particle capture, but Chapter 14 concludes the text by detailing a phenomenon where emission induces extreme localized physical destruction, the hot atom nuclear reaction.
Specifically, the mechanics of the Szilard-Chalmers reaction. To understand the sheer kinetic violence of this reaction, you have to apply the macroscopic laws of classical physics to the quantum realm, the conservation of momentum.
When a target element captures a neutron, the newly formed isotope is in an incredibly highly excited energetic state.
To quickly relax, the nucleus violently fires off a highly energetic pumped gamma ray.
The law of the conservation of momentum states the total momentum of a closed system must remain constant. If you fire a heavy caliber rifle, the forward momentum of the bullet generates equal rearward momentum. The recoil kicks the stock into your shoulder.
This identical mechanical principle applies to the emitting atom. When the nucleus fires the high-energy gamma-ray photon out into space, the physical mass of the atom itself experiences a massive instantaneous kinetic kickback.
The physical atom violently recoils. The critical aspect of the Szilard-Chalmers reaction is calculating the specific magnitude of this recoil energy.
Using the equation equals E gamma squared divided by 2mc squared, the kinetic energy of the recoiling heavy atom is frequently on the order of several hundred electron volts.
Which reveals why this reaction is fundamentally destructive to the molecular architecture. A standard chemical covalent bond holding an atom to its neighbors requires roughly 2 to 4 electron volts of energy to break.
The gamma emission generates a localized recoil energy of several hundred electron volts. The kinetic kickback is orders of magnitude more powerful than the physical strength of the chemical bond holding the atom in place.
The physical consequence is absolute localized structural failure. The physical recoil of emitting its own radiation causes the newly radioactive atom to violently tear itself free from its chemical bonds.
It literally shoots itself out of the parent molecule. The newly formed radioactive isotope is violently separated from the surrounding matrix of unreacted stable parent molecules.
It becomes a free, highly kinetic, unbound hot atom floating independently in the solution, completely stripped of its original chemical identity.
The pragmatic application of this violent recoil in the radiochemistry lab is profound. Because the radioactive hot atoms have shattered their own bonds and altered their chemical state, they have done the difficult separation work for the researcher.
Instead of spending days designing complex thermodynamically stabilized ion exchange columns to separate a microscopic fraction from a massive bulk of stable isotopes,
The researcher can simply utilize a basic chemical extraction to harvest the liberated hot atoms.
this elegant exploitation of quantum recoil allows scientists to efficiently extract newly synthesized isotopes with incredibly high specific activity in a fraction of the time.
The atoms physically liberate themselves from the chemical matrix through the sheer violence of their own energetic creation.
The utilization of the Szilard-Chalmers reaction is the ultimate culmination of the author's intent. It bridges the theoretical mathematics of quantum momentum with highly efficient laboratory technique.
Mastering the underlying physics allows the researcher to manipulate the chaotic realities of the nuclear environment to achieve incredible analytical precision.
Which brings us to the conclusion of our journey today. We have thoroughly disassembled the mechanics of nuclear chemistry.
We began by honoring the deep historical roots with Acharya Kanad, proving the drive to map the fundamental building blocks spans millennia.
We moved inside the modern nucleus, exploring the quantum architecture of the shell model and the thermodynamic quest for stable magic numbers.
We dissected the mechanics of detection, trapping invisible radiation using cascading electron avalanches in argon gas, specific photon flashes in a scintillator, and engineered quantum band gaps in semiconductors.
We rigorously analyzed the physical illusions and statistical hazards of the lab, mathematically proving how self-absorption hides radiation behind saturation thickness and how adding an inert carrier normalizes it.
We utilized exponential decay equations to identify unknown isotopes using lead shielding. We mapped the fatal trenches of standard deviation using the river crossing analogy.
We acknowledge the biological consequences when this chaotic energy severs chromosomal DNA.
And we explored the pinnacle of separation science, from Chopin's ion exchange column to the kinetic violence of hot atoms snapping their molecular bonds.
It is a massive amount of highly complex information. But recall our primary mission for you, the learner. By unpacking the fundamental why driving these detectors, the sample prep, and the counting statistics,
You're no longer memorizing isolated equations. You possess the comprehensive skeleton key. The dense academic jargon is merely a descriptive wrapper around these specific physical realities.
you are intellectually equipped to open any advanced scientific textbook and comprehend the practical, chaotic, and profoundly beautiful mechanics inside the radiochemistry laboratory.
As we conclude this deep dive, I want to leave you with a final provocative thought that extrapolates directly from our discussion on the extreme kinetic recoil of the hot atom. Think about the fundamental nature of the physical reality you occupy right now.
It's all connected.
Exactly. The entire macroscopic world you can touch and see, the solid desk in front of you, the structural integrity of the device transmitting this audio, is ultimately dictated by the constant, invisible, stochastic interactions of atoms occurring just beneath our perception. We exist in a physical reality where an absolutely unseeable, massless photon of electromagnetic energy possesses sufficient physical momentum to literally snap the covalent chemical bonds of its own molecular home through sheer localized recoil. It forces a profound question. If the seemingly solid, stable matter of our macroscopic world is essentially an illusion painted over a chaotic quantum battlefield governed by shattered bonds, random statistical variance, and the thermodynamic drive toward magical energy numbers, what other massively energetic, highly disruptive interactions are occurring constantly in the invisible spaces around us right now, simply waiting for us to engineer the precise mathematical framework and the correct physical detector to finally observe them?
That is exactly the kind of question that drives the next century of scientific discovery. The invisible world is vastly louder, infinitely more complex, and significantly more physically violent than our macroscopic senses suggest. Thank you for committing your time and focus to taking this deep dive with us today. Keep questioning the fundamental architecture of your reality, keep expanding your framework, and we will catch you next time.